Okay, continuing on today with our Laplace transform playlist, we have here a second order homogeneous differential equation on the board. We've got y double prime plus 6y prime plus 73y equals 0. And we have these initial conditions, y at 0 equals 1 and y prime at 0 equals 2. So to get started with this, we'll do what we've done in the previous videos on these, and we just want to start by taking the Laplace transform on both sides of the equation. So on the left side of the equation, what I'm going to do is we can actually break it up. So we'll have our first term as Laplace of double y prime. And then here we're going to take out a 6 in front, and we'll just have the Laplace of y prime. And then here I'll take a 73 out front, and we'll just have the Laplace of y here. On the right side of the equation, Laplace of 0 is just 0 because it's an integral. You plug 0 into an integral, you just get 0. And then to simplify everything we have here, we have these formulas that we found in previous videos on the first derivative and second derivative. And we also have our initial conditions that we'll use in these formulas. So let's just see how it goes starting with the second derivative. This is going to give me s squared, big Y of s, where the big Y of s is just the Laplace transform of y. It's just the same thing as this here. Then we're going to have minus s times y at 0, which is just 1. So we'll just leave that off there. And then we'll have this piece, which is just going to be y prime of 0, so this is going to be a 2 here. And then we're going to have 6 distributed into this formula. We're going to have 6s big Y of s. And then we're going to have minus distributing the 6 in times 1, but we'll leave that off. And then for this last piece, we're going to have just 73 times Laplace of y, which is just the big Y of s. But then from here, what I'm going to do is let's just take, we want to isolate this big Y of s because that's going to get closer to finding the y value. So if we isolate that, so what I can do is factor out that big Y like this and then collect all the terms. So we're going to have s squared here, we're going to have a plus 6s, and this is going to be a plus 73. And then for minus 6, minus 2, and minus 6, I can take that to the right-hand side of the equation, just adding it on both sides. So adding an s, we'll have an s here. Minus 2 times minus 6 is minus 8. Bring it on the other side, we have a plus 8. And now in order to solve for our big Y, I can just divide here by this whole thing. So we'll divide by s squared plus 6s plus 73 on both sides. This is going to cancel here. So now on the left-hand side of the equation, we're just going to have our big Y of s. Now for this thing, we can't really factor that denominator, but we can complete the square. Because 73 is such a large number, the discriminant would be negative, and so we have no real roots on this. But completing the square, I'll take half of that 6, and what I can do is write this as s plus 3 squared. If you multiply that out, you get s squared plus 6s on the middle terms, then plus 9. Well, in order to get to 73, I can just add 64, because 64 plus 9 gives me 73. But now at this point, to solve for y, I can just take an inverse on both sides, take the Laplace inverse here, and then I'll just kind of write it in there to show what we're doing. Because big Y of s is just the Laplace of y, and then we take the inverse Laplace, that's just going to give me y. So to solve for y and get our answer, all we need to do is we just need to find the Laplace inverse of this whole thing, s plus 8 over s plus 3 squared plus 64. So let me just clean up the board, we'll solve this thing and finish it off. Okay, now from here, we just need to work on this inverse. And what I can do, because we have addition in the numerator, I can actually split this into two separate inverses. So for the first one, we'll just take our s in the numerator. So this is going to be s over s plus 3 squared plus 64. And so for the second one, we'll just have this 8 in the numerator. So we'll have Laplace inverse. We'll have 8 over the same denominator. But now at this point, each of these Laplace inverses aren't too bad. We just need to use a few formulas on these. Okay, now first looking at our first inverse, this one right here on the left. Now just notice this is really similar to our formula for the Laplace of cos AT. We have the s in the numerator. Our a squared here, we can write 64 as 8 squared. So our a value here is going to be just 8. The only issue is we have this kind of shift going on here that we'll have to consider in a second. And then for this second one, just notice this is really similar to our sine AT formula. We have, again, if our a value is 8 and this is 8 squared, we'll notice we want this a in the numerator. Well, we have our 8 right there. So this is going to be really similar to sine 8t, and this is going to be really similar to cos 8t. But we just have to consider this shift here in both cases. Well, for s plus 3, we can actually write that as s minus 3. And so just looking at this formula here, this is the same shift that's created if we have e to the minus 3t multiplied by f of t. Because if we look at that Laplace transform using this, we just end up with f of s plus 3, and that's the exact shift we have right here. So if I just multiply by e to the minus 3t here and e to the minus 3t here, so this is going to be exactly the shift we need to get this s plus 3 in here and s plus 3 in here. So we're really combining this formula with these other two formulas. But now before we finish it, there is one problem. We have this shifted by this minus 3. We have this shifted by this minus 3, but we haven't shifted this s right here. So what I can do is force the shift to happen here by just adding a plus 3. But I don't want to change it, so I can subtract 3. But I won't do it here. I'll do it over here. I'll subtract 3 over here. So then 8 minus 3, we're going to have 5 in the numerator over here. So let's just write that in. So this one here is shifted and it's all set up perfect. But this one still has a problem because we need a here in the numerator. So we actually don't want a 5 here. We want an 8 here. So what I'm going to do is I'm going to factor a 5 out front, put that here, and then I'll create this 8. But so I don't change it, we'll divide by 8. And now this inverse is perfect. It's in exactly this form with our a in the numerator, a squared here, shifted by minus 3. So we just had to pull a 5/8 out front. So putting all this together for the final solution, we'll just copy everything down. We have e minus 3t cosine 8t. Don't forget the 5/8 plus 5/8 e minus 3t sine 8t. Put a plus c, and that's it. Okay, no plus c. So there you have it, second order homogeneous differential equation with Laplace transforms. Thanks everyone for watching. Have a good day.